Hello, everyone. Welcome to this morning session and to the, well, second, third, whatever day. The definitions are confusing, but you know, programming, one of the hardest programming problems is counting things. So I think we're off by one somewhere in here. We're going to overflow on Friday or whatever. But here's our first speaker, Renan Dincer from Cloudflare Engineering Manager, and is going to tell us everything about Anycast challenges and using it for real-time media. It's a subject that's very close to my heart because we have an Anycast network internally, and we're still trying to figure it out how it really works. Some of them is actually non-deterministic. So very much looking forward to your talk.
Cool.
Take it away.
Hello, everyone. My name is Renan, and I work at Cloudflare. I was actually gonna. Oh, thank you.
First speaker, second day.
Yeah. Who knows what Cloudflare is? Like, can I ever raise my hands? Okay. Who knows what Anycast is? It was mentioned a lot in the previous. Okay. I'm gonna try to describe what both are. So don't worry about it if you don't know. But the talk is about. Oh, this is my other slide. The talk is about we do these things all over Anycast all the time. And the talk is about, how does this work? But what is Anycast? Before I talk about Anycast, we are familiar with broadcast. And broadcast, in the US you have cable. There's a cable that goes into your house that has all the channels all the time flowing through it, TV channels. And then you have terrestrial, like more common in Europe, where things flow all the time, radio is that. And when you have radio, when you have this thing, a lot of data is flowing all the time in the air. You don't have to request it, you don't have to touch it, you just tune into it. And even if you're not listening to it, it's in the air. And things are traveling all the time, which has interesting limitations, like you can have so many channels. And that kind of defined our culture a lot, going back, and that limitation. For example, and I saw this recently on Twitter, where the viewership for one of the examples was President Nixon's resignation speech. The other one was the launch of the space shuttle. They got 140 million viewers at the same time, while it was comparing it to Succession, which people think, oh, it's a culture phenomenon. It got like less than 1 million, I think, or 2 million, something like that. So the numbers have fallen because we have the internet. The internet is great. Internet is very different from broadcast because you have unlimited options. Things flow both ways, and you can request things and get things back. And you can do cool things like, you can go into your TV and watch Kardashians season 5, which is 2010. And you have everything available to you all the time. You don't have to wait, for something to happen. When you connect as a user to a server, you do it over IP, and you get something like this from DNS, and then you just connect to it. And if you go to Amazon, you'll see this IP address displayed here. I have a server here. It's a virtual server. But I have a server here, and then has an IP address. And, it's very common to do this. People do it all the time. You probably do it at work. And, people have public servers, and then you can, I don't know, SSH into it or whatever. And then do whatever you want to do. So when you have, multiple servers, you have different IP addresses in them, and you can do different kinds of things. And you can reach these things, and you can put a load balancer between them so that, your load goes across from them. I've been tagging what these things are, but I'm gonna get to that. But, when you're talking about, when you're connecting to all these IP addresses, I, put an arrow here saying, oh, you just connect to the IP address. But what does that really mean? In reality, the previous talk was a great example of this because, you saw what these things actually look like. But there's, your Wi-Fi machine, and then it goes to a router, maybe I don't know, down the street or whatever, and then goes to the a bigger data center, maybe has a fancy 400 gig like in the previous talk, connection to another router somewhere else, and then maybe another router, and then it goes to the server. And these routers all communicate all the time, so that when you send a packet, it goes there and it knows where to get. In reality, there's a lot of routers around the world, and they're all connected to each other. So the path actually looks like this. And these routers are connected in very random ways defined by geography and how people are spread around and what people use computers for. For example, in an office, you might have a router on every floor and then a bigger router downstairs that has a big connection going out. But if you're in a residential area, you might have a different setup. These things change, and you can't really map these things apart from saying it's kind of organic. Depends on the use. And again, there's different paths. Your Wi-Fi machine might talk to your ISP, and then ISP might talk to the data center, and that data center, it doesn't talk to here. But if you want to go to here, you go here, or you can take a longer path there. But there's different paths. And actually, kind of funny question, but what is the internet? Internet is just the internet with a capital I, because you can have private ones too. If this is private and you all own it, that could be your internet. But internet, capital I, is just these things all interconnected. And it's a fantastic human achievement because we got to connect these things. It kind of looks like this. Technically, you can't actually map this like this, but people did a lot of good attempts. And each dot is a network that talks over the public internet. And there's many cool pictures in that link. But these things are very well connected, and every color is a continent. So as engineers, there's this communication problem, like what protocol do you communicate between these things? And there's a protocol for that. It's called BGP, Border Gateway Protocol. And what you do is, if you want to be on the public internet, which you want to be, you go to an organization called IANA, or someone connected to IANA, and then you tell them, oh, okay, I want to connect to the internet. Please give me an IP address, because that's what we use to talk to things. And they give you a range of IP addresses. Nowadays, they will, if you want it for free, you just get IPv6, but you can also get IPv4 from others, and you get, kind of like domain names, an IP address range. And then you get a number. And there's a whole protocol where you can talk to other routers and start doing things over the internet and start sending packets of your own, and then you can start relaying packets depending on what your role is. And your role can be anything. You can be a ISP, carrying data from residential neighborhoods to places. You can be a data center operator. You can be anything you want. And there's fun things you can do with this as a hacker. For example, a colleague of mine, got a bunch of IP addresses and runs a bunch of things, and he knows, okay, this is not going to go away, or you can do cool things. So the other thing you can do, when you have this, because we talked about in the, many slides back, you go from there to there, and every machine has an IP address, and then there are different IP addresses. The other thing you can do is you can put machines a lot of places, and you can place them strategically or kind of randomly, whatever you want. And when you put these things, you can give them the same IP address. And if you this is a real IP address that if you dig my personal domain, you get this IP address, and you get this IP address everywhere. And there's actually many machines. Your computer doesn't do that. Your computer doesn't know that there are many machines, because when the Wi-Fi machine when your Wi-Fi machine talks to the router, it says, I'm going to go to this IP address, and then this router will say, oh, cool, I know a path to get there. It's this way. And it doesn't know that they're actually everywhere. And if you go to this router, it'll say this way. And if you go to this router, it'll go this way. And if you say this router, it'll say it'll go this way. And one of the things that BGP does is it allows you to find the best is a interesting word, but a word, a path to get to where you want to go. And the closest way as defined by network hops. The shortest way. Did I say best way? Oh, sorry. And that's what Cloudflare does. Cloudflare has a lot of these locations around the world, and they're all broadcasting. They're telling, oh, I'm this IP, and they're giving all the IPs. And if you're ISP, I don't know, if you're a barn, we have a place in Manchester. Maybe you go there. And then if you're also, an ISP, you can configure your router saying, okay, I want this traffic to go there. And kind of that relationship is called peering. And there's good websites you can look up, where do I peer, or where does my ISP peer with other places. And you can find out, where your ISP connects to, say, Netflix or Cloudflare or Meta, whatever. You can find these things out. So this map, when you put it kind of in practice to the route, from Cloudflare's perspective, kind of looks like this. There's the internet, and then there's many ways you can reach Cloudflare. And Cloudflare is a business. Cloudflare's business, this is what I say, and I think it's the best way to describe it. Many people will describe Cloudflare in different ways. Cloudflare's business is to get machines and put them in places very close to users. And the number is, we are 50 milliseconds away from 95% of the connected population. And that's what we do. There's metrics you can monitor, and then you can put more boxes in places where it's needed. We do many things with this setup. We do authoritative DNS, so you can put your website and change your website's DNS to us, and then we'll serve your DNS. We do recursive DNS, which is what you put in your router or in your computer. 111 is an example of that. Famously, we do DDoS mitigation. The cool thing with Anycast is that if you have a distributed denial of service attack, given that it's distributed, and if you're against a distributed system, the attack will be smaller at each location instead of just all going in one location. So that's a effective way of kind of mitigating these attacks. We also mitigate other attacks, firewall stuff. We are a HTTP proxy. A large chunk of internet flows through us. Cloudflare started as a kind of performance company. People want to put copies of their website close to users where they can be served. For example, if you're a newspaper in Australia, and if you have a lot of visitors coming from the US, or if you have nobody come from the US and Europe, you don't do anything there. But then if one day there's an event, and everybody visits your website, they get copies of it elsewhere without having to talk to Australia, which is far away. We also operate edge compute stuff. There's many products that Cloudflare does. Cloudflare has. It's called Cloudflare Workers. You can run JavaScript on it. Hugely popular website for ComCon is on Cloudflare. Many different things is on Cloudflare. What is in Cloudflare? You might ask. So this is a router that whatever other routers talk to, and inside the Cloudflare data center, there's many servers, and these servers also have the same IP address. Everyone has the same IP address, and this router is kind of an entry point. But there's every machine runs every service. So one machine at the same time might be serving 111 DNS stuff while doing edge compute stuff, while doing HTTP proxying. And the reason kind of we do this is because, there's many reasons. Both in the data center and outside the data center, you have automatic failover options. For example, if fiber gets cut or something, BGP will automatically reconfigure itself, and it'll go to where the closest location. No, what did you say? Closest location by network hops. Yeah, shortest route. Thank you. DDoS resilience, I talked about that. You can have uniform software, scale. By scale, I mean like there's a small factory that makes these machines and and then we ship them to places and then place them on racks and then connect them, and it becomes very easy as opposed to having like very custom hardware that needs to be custom made. They just make it and then we put it and then same software goes on everything and you don't have to think about it. But one of the biggest thing is, and what Cloudflare usually optimizes for is performance. The 50 millisecond from many people number is very important and kind of helps with a lot of different things. For example, if you have a website and the website server is close to you, you need to have a certain number of hops to establish, for example, a TLS connection before you start downloading the website, and it reduces that latency. Or if you use us as a security proxy like VPN, it increases your speed and your performance. So there's a lot of things you can do that requires performance. So going back to media, so that is Anycast. That is my kind of best explanation that I came up with. A lot of people will have a lot of different explanations for Anycast and analogies, but that's kind of what we do. And this talk, media, we do these things, which kind of boil down to these things, because RTMPS, HLS and Dash are kind of over HTTP, which is over TCP. RTMPS is also over TCP. Kind of boils down to this set of protocols. So I want to talk about these things and kind of like how they generally work. And then if we have time, I don't know when this talk is supposed to end. I think because we started late, right? If we have time, we can answer questions and dig deeper because it's a very technical audience. So TCP, we do media stuff at live.cloudflare.com, this port, and everywhere listens to this port. We use a layer for load balancer in front of kind of TCP. I'll talk about it in a second. So one of the things people talk about Anycast that's problematic is, oh, what if the routing changes in the middle of the session? And what if BGP reconfigures or if fiber cut happens or something happens? And that's one of the reasons why people don't deploy Anycast, because there's more unexpected situations versus if you have routing controlled by DNS or routing controlled by something else, you have more predictable places to go. So it becomes kind of an operational concern. We do a lot of things to reduce that, and very often you get from here or you're from your home, which Cloudflare you go to is very often very consistent. And it doesn't change much. When it changes, you don't notice. For HTTP, requests are very short-lived, and your browser does enough to retry these things, so you don't notice them. And for RTMPS, we rely on the reconnect logic to get to Cloudflare. Within Cloudflare, as I said, we have a layer for load balancer that load balances using the for tuple, so inbound IP port and your source IP port of the packets. Load balancers usually look like this. So you have a separate machine that load balances things. At Cloudflare, it looks like this. There's a blog post about it that you can learn more about. But basically, the router does its best job equally distributing packets across all the machines in the data center, and then the data center things forward to each other so that processing can happen. And this is a bunch of benefits. I had a list of benefits. But this is a bunch of benefits. For example, you can have, when you want to take out one of the servers out of rotation, you can take them out and service them. You can load balance between, differently load balance between machines that perform differently. You can do many different things with a load balancer in front. And you can have kind of consistent routing of packets between servers. We also do SRT, which is a little bit easier because that's where we do SRT. SRT is a protocol that carries media, and it's often used in broadcast where you send packets from a device like, that they might have at the back of here, and then to a server for broadcast. They use UDP and, again, consistent routing in the data center because it has, it's just UDP and you can look at the 4-tuple. And one of the cool things is you can CNAME into it because since it's UDP, you don't care about certificates. You can also CNAME using RTMP, but we have to issue you certificates. But the great thing is RTMP has this too, in-band signaling of media and signaling stuff only on one port, which makes it very easy because everything goes to the same machine and you can handle it there, which is not the case for WebRTC. You have out-of-band signaling, you have a bunch of different protocols, they operate on different ports, and everybody assumes that when you connect to when you do WebRTC stuff, and I haven't seen anyone do WebRTC over Anycast before. If you do, let me know. You have to deal with all this. So kind of how does that work? With SRT and RTMP, everything always goes to this right machine in the data center. But with WebRTC, signaling stuff will go there. WebRTC stuff will go another machine. These machines need to talk to each other, coordinate each other. So how do you do that? There's several ways you can do it. I'll talk about different solutions. So one of them is you can have a server in front or a service or something that sits there and does signaling. And sorry if you're colorblind, but the left side is one color, all the arrows, and the right side is different colors on the arrows. I should have done that better. I didn't think of it. The colors represent, so when you have an offer come in, what the answer might be. But the signaling server doesn't know what to choose. So for example, you might have an offer coming in. It goes to any of these machines. You can send it to all of them. And you will have different answers because you have different SSRC randomness there. And then there's randomness that comes from DTLS certificates. Like, how do you deal with that? Signaling server doesn't know what to choose. And if you once you pick it and once stun packets come back to these machines, most of the machines, and some data centers have hundreds and some data centers have only a few machines, will get unused stuff happening to them, and it's unnecessary kind of capacity used. So you don't know. So one thing we can do is we can come up with those random values ahead of time. So in the signaling server, you can say, oh, okay, this is the certificate you should use, and this is the randomness you should use, and distribute it to all the machines. And then when the ICE packets come, they can deal with it and send a predictable response. But again, not very good because you don't have machines that machines do things that you don't. That is unnecessary, and they will just time out, and they will have weird state, and it is annoying to deal with. So what we do is a little bit different. What we do is we come up, when you first send the offer, we pick a machine, send that to the machine. The machine will generate an answer and create the randomness, and then photos being taken, and then it'll give the answer. And then we'll save whatever kind of randomness there is in the copy of the offer somewhere. And then when this comes in, you're like, okay, this is a packet that I haven't seen before. I don't know because this machine is not that machine. And it will go and say, okay, I can look up the username from this packet, figure out where, what this packet is, what the history of this is, what we said to it, get the proper answer, and return it. And then, when you do DTLS, things just work and go to that machine because everything starts going to the same port. WebRTC hacks complained about this because we have a bunch of problems that we're trying to solve, and they said it is too slow. We've since improved this a little bit, but again, this kind of on-demand generation of things take a little bit more time. So that is one of the penalties that we're eating because we want to make things as fast as possible, and we don't want, on this path, on the kind of steady state when things are going, we don't want to have performance penalties here. How do we deal with aggressive nomination trickle-ice? This was a big issue over time because the machines will send a lot of packets at once, and they will go to different places. For example, if your browser might do IPv6 and IPv4, and it is very likely that IPv6 might be higher on the list of being picked, but IPv4 might return fast because some reason. So how do we deal with this? So when packets come in, there's these, and that thing kind of needs to be a source of consistency. We use, this is not secret, we use Cloudflare Workers, which is our edge computing product, and it has a tool called durable objects. And what it is it's a single threaded process, which makes sure everything is kind of transactionally guaranteed. And it's a storage thing because it's kind of single threaded and kind of long lived. So everything connects to that, and single threadedness solves the order issue and saves all the details it receives, and then sends, and saves all the history of the different offers, and we can, send whatever state's required and send the right responses to all the packets. Again, slower than having it all in memory in one machine, but it pays off in the end. And kind of Cloudflare Workers, all this logic is built on Cloudflare Workers in JavaScript, and kind of we use the storage that comes with it. But this is something you can just buy, and many people use it. So the other interesting thing that we do is how do we deal with software updates? So there's a lot of machines, and they all have to be updated, and you cannot wait for the session to end. So we use something that we blogged about again, and this is open source. But what we do is there's all this state, and when a software update to the machine comes in, we launch another process right next to this process, and then exec to that process from the main process as it's going, and transfer the state in the meanwhile. Takes a few milliseconds. People don't notice, but you have new software taking all ownership of all the state comes in. And then we go and set up the peer connection and all the structures that needs to be set up in software from the offers that we got, and just replay them, and then forcefully transition the state of the connection, the peer connection, to connected. Once the once the new process has launched. So everything looks normal, and it takes like a millisecond or two, and your packets might be slightly delayed and queued as that is happening, but people don't notice it. And that's how we do upgrades of software, kind of when everything is live and everything's operating at the same time. So, okay, what are we doing with this system? Like, what, we have all these protocols, we have WebRTC, whatever. So what we're trying to build is a system that is kind of different from other systems. I tried to describe it to a bunch of different people in different ways, but I'll give you an example from broadcasting. And then, same thing applies to bidirectional communication. You have a broadcaster, so in New Jersey, and then you have viewer. Since Cloudflare is very close, they terminate very close, and then we can use the Cloudflare backbone that we control and that we kind of keep the health checks and whatever going. Keep the link clean. So you can have media going from this side to this side. And then if you have, this is kind of broadcasting, but works over kind of WebRTC, SIT, RTMP, whatever. You can have it kind of fork to Paris if you want to view it from Paris. And again, this is network in, network out. So the latency you're adding here is the speed of light, whatever is required, which is the minimum because you can't get faster than speed of light. And if you have another person come in and they talk to another server randomly, you can deduplicate locally. And then you can like create a tree structure. The more people you come in, the more likely it is that they'll land to the same machine that somebody else is viewing on. And then you can start sending data there. And you created this kind of tree structure that kind of follows logic where all the machines ask, okay, is the flow on the server, if not it's in the data center, is in the same region, and then if not, go to the source. Find the source and retrieve it from source. And the cool thing you can do is you can be arbitrary directions from arbitrary ways, because all these machines are the same, they're everywhere, they're all connected. So you can kind of have media flows going one way or the other. You can have the concept of a video call, but there's no concept of a room. So you can have arbitrary kind of things subscribing to different tracks that are just available in the world. And kind of instead in traditional kind of content delivery network, there's a predefined set of kind of tiers. Instead of following that, you can make something random. And this allows you to kind of create all the different kinds of experiences that are not really possible with a traditional SFU because you can't scale from one machine. But also you can't use a content delivery network because it's kind of very fixed. So all kinds of different things are possible. And in a single service, because all these machines are running the same software, they run the same services, they just literally open the same port. You can push media, and then kind of the durable object sits between keeping track of the state. And then, that registers itself, and then other people find it and register themselves. And as long as there's a listener, either another server or a customer, that keeps the media. And kind of there's no SQL, there's no centralized storage. It's all kind of edge native stuff. And this whole thing is integrated, the WebRTC, SRT, RTMP, this whole thing is integrated together. And they turn media into a common format. For example, if you're, this is just Golang readers and writers. Reads it, writes it. If you want to pull it, pulls it for you. Or if you want to go to HLS and Dash from these things, goes that way. R2 is our storage, like S3. And also a product we sell. If you want to push it elsewhere, you can also go this way. So there's like many paths you can form in this structure, in this distributed system. And you can do interesting things with it. And this is my connection in New York City. And all the performance work and stuff we're doing, you can get 2 milliseconds ICE responses in the stats. So a lot of work goes into making that number very, very, very low, but you can power very interesting experiences over the internet. So any questions? Yes?
The slide on the detail is just a mandate that because of Anycast being in the Cloudflare,
Yeah.
the server cannot initiate the client hello?
So the outbound is not Anycast. Outbound is Unicast because when you do, well, that's not always true. There's a blog post about it, Google it. But some of Cloudflare does Anycast outbound as well. But most of it is Unicast outbound so that the return path knows what to return. Just the inbound path is Anycasted. Good question though. Yeah.
So we're using Cloudflare.
Yeah.
And it's great for TCP and other stuff, SDCN, but
Yeah.
what do you do? How can you offer DDoS protection against UDP attacks?
Yeah.
I know you had the bandwidth
Yeah.
case study, maybe you can share
Yeah.
results from there or whatever you can
Yeah.
tell us about the ability to protect from UDP attacks.
Yeah.
DDoS UDP attacks.
I'll repeat the question for the internet. I'll just read it. How do you defend against UDP attacks? Is the question. I'm not an expert in this. I'm a media person. There's many people at Cloudflare who work on that, and actually a lot of that work is on our blog. But the gist is, it's not just kind of Anycast. There's other systems that filter things, depending on what layer they're And UDP attacks are definitely a thing. TCP attacks are definitely a thing. There's many different kinds of attacks, and kind of there's different levels of defense you can have. Yeah.
So a similar question is, in my own.
The microphone.
Thank you. A similar question is in my home office.
Yeah.
Whenever I go to just a website,
Yeah.
some shopping websites or whatever, I usually get this Cloudflare check, DNS
Yeah.
check.
Yeah.
And then they used to be more transparent, but now sometimes they require me to put a check mark
Yeah.
or prove that I am a human person or that sort of
Yeah.
thing. And this is really becoming a pain in the ass.
Yeah.
I mean, really, it's because each time, and especially for my wife or
Yeah.
my kids, how can I avoid this?
Okay.
I thought my ISP was blacklisted or something,
Yeah.
but then I was in Germany last week. It happened to me a few times there
Yeah.
in the hotel network. It happened to me here as well a few times. So looks like you guys are either gone crazy or you are very picky.
We haven't gone crazy. There's many reasons. There's many reasons why that might happen, as you would expect.
Or you are getting more customers. I don't know.
No, I'll give. So one of them the website owner might have turned a higher security mode that forces that on. Another reason might be that kind of depending on different kind of many reasons depending on different kind of ISPs configurations, whatever, it might be deemed higher risk. There's ways you can get across that. There's like a bunch of fancy crypto ways you can avoid that, and there are technology solutions to this, but none of these are satisfying answers, because if there was a satisfying answer, we probably would have just done it. So sorry about that. There are blog posts about this, and yes, I hate them too.
Questions from the audience? Cool, Dan. Well,
Cool.
sounds like this is good. Well, thank you for your talk. That's
Yeah,
great.
thank you.
Keep it up. Yeah, and about UDP, I could tell you a UDP joke, but you will get it. Thank you so much. There's a coffee break coming up, and we have about 15 minutes, so I'll wait for you here in the quarter hour. Thank you.